So today I will be presenting on the topic support vector network. But before knowing what is support vector network, we should know what is support vector machine. So first we should have a preliminary knowledge about what is support vector machines. So actually, support vector machines are one of the best, actually the considered to be the best of the shelf supervised learning algorithm, and this is cited from the notes of Stanford. And now this page, I will be coming back to this letter to explain what I have written in the below line. The optimal hyperplane weights are the linear combination of support vectors. But first of all, what is a optimal hyperplane? So basically, as you can see in this figure, we are having two sets of data, the crossed ones and the circular ones. And this data can be divided into two parts by this hyperplane. And this hyperplane actually divides this in such a way that there is no error in this. So this will be known as the hard margin SVM, because this margin is hard in its own and there is no error in the training examples. But and what is this? These are the optimal margins that we get, and our objective will be to maximize this optimal margin so that no data points are nearer to each other, such that we have a strict distinction between the two sets of point. And this is actually a binary classification problem, as you can see in this figure. So this is done in a two-dimensional space, but this is always not the case, and we can have a higher dimensional space. That is why we are not writing it as an optimal line, rather we are calling it as an optimal hyperplane, because it can be a plane, and in higher dimensions we will be calling it as a hyperplane. So after that, what if the data points can never be separated by a straight line or a plane? So what we will actually do is we will map these input features to a high dimensional feature space, or a non-linear function will be applied to this input space to get a new feature space, such that these feature vectors can be separated by a hyperplane. And again, if we map this back to the input space, we will have a non-linear segregation, because this is a non-linear separation, as we can see in the figure. So now here, this is actually a support vector network. So this applies the idea of support vector machine on each of these nodes, so that we can classify each of them and use that to formulate a network which works on the principle of support vector machines to get that. And so what are we actually doing? We have this input vector x, and we are applying a non-linear transformation to get another input vector which is in a feature space. And this feature space is a transform feature space which we had the input vector in. And now we will apply our classification model on this feature space, and then we will classify the object. That this will actually, what why actually we will be applying this nonlinear transformation? To reduce, actually to reduce the uh, amount of computation that is required to classify this. Because if after some slides I will be showing why actually the computation is actually getting reduced while we are applying the transformation here. And actually, separation without errors in training data is also impossible in the real world case. So that is why we will be talking about the soft margin SVM rather than the hard margin SVM. So the actually the three main concepts we are divided into four parts. That is the what is optimal hyperplane, the soft margin hyperplane, the kernel, and the convolution of dot product in feature space. These are the four main topics that are related to SVM and SVM. So now this is the case of a hard margin, and you can see that there will be no error in the original training data samples that we have, and the margin value is to be as high as possible. And this is actually an optimization problem to maximize the distance between the two margin that we obtain. And we will also have to minimize the loss for the data points that we have in our data set. And this is a soft margin hyperplane, and you can see that error in the training data with margin value is also taken into account, and there will be some errors that will be accounted in this. uh, Now in this case we can easily show that in the hard margin SVM you can see that there is no error in the training sample, that all the red are either on this margin or on the below this, and all the blues are always above or on the margin. But now in the soft margin case, you can see that there are some points that are wrongly classified here. Even though they are in the training examples, they are being wrongly classified. Like this one is in this area, but it is classified to be as red. So that is why it is wrong. But even though it is wrong, it is being taken into account. So this is the soft margin SVM case. And actually this is taken into account because we have to find a sweet point where we do not have too much of computation, and neither we lose the differentiation ability of the machine. So now I'll be defining what is a kernel. So basically kernel is the mapping from one space to another space. And why we will be needing a kernel, I will explain later on. So now let me move to my uh, the paper and see why the about the optimal hyperplane first, and then I will go to the kernel paper. So actually you can see that our training data is labeled as like yi and xi. So the yi are the labels and xi are the input vectors here. But now what we will be doing is that we will define some constants here. This wi xi plus b, actually this line, I have the diagram here, this one. So actually here you can see that this line is the wx plus b equals 0. Whereas this upper margin can be taken as a wx plus b equals 1, and this the lower margin can be taken as wx plus b is equals to minus 1. So actually what we are doing is that we are applying the constants on these data points, and these data points are actually written in this form, that the wx plus b should be greater than 1 if yi is greater than 1, and we are taking this upper portion to be the positive class, and this, actually we are defining it to be plus 1. So it should be greater than plus 1, and the below one should be less than minus 1. So this is what we are defining here in this constants. And now to get a closed form of these constants, we are just writing yi. So this gets multiplied with this one, and then we will get yi into w into xi plus b is greater than 1. So this is the closed form of the constants that we have in this is a hard margin SVM. And now we have the optimal hyperplanes equation, w naught x plus b naught is equals to 0, and w naught and b naught are the trained weights that we have for our model. So now you can see that here, if we take this to be the optimal hyperplane, you can see that the in 3 dimension or according to the vector notation, the perpendicular to that plane will be the w cap vector will be perpendicular to that plane, and it will be moving outside. So if we calculate this distance, it is actually 1 by mod of w, whatever be this w. If we calculate this distance between them, it will be 1 by mod of w, and the total margin that we have is 2 by mod w. So what we can define it is, we can define it as 2 by root over w transpose. Actually the dot product can be written in the form of w transpose, that is why we can write this. So actually what we have to do is we have to maximize this value. So to maximize this value, we can say that we have to just take the norm of it, square it, and minimize this value. So if we minimize this value, we can actually
Asmit,
maximize. Yep.
uh, WW transpose is not a scalar as far as I see.
uh,
I think it should be W transpose W or something.
oh, so, sorry about that,
Yeah,
I just missed it. It is
yeah,
actually
no
w
problem.
transpose. So that is a norm of w squared. This should be minimized as much as possible, such that the margin is maximized between the two optimal margins that we obtain. So after that, this is what is written over here. And now what we'll be doing is we will be considering this problem as the primal problem to minimize the mod w squared with respect to this constant. But if we apply the Lagrangian dual on it, then we can easily solve this without going without having a large amount of computation. And why we can see, due to the vector size, if we calculate the vector size, it will get to a point where the number of vectors that we originally have is actually np, but when we have the Lagrangian dual, it will be of n squared, and this p value is so high that it is actually p will be greater than n. So that will result in lesser computation when we have a Lagrangian dual applied to it. So if we transform that to a Lagrangian dual, equivalent dual problem, and solve that one, we will be easily able to find the solution in lesser amount of time. So what is a Lagrangian? Everyone knows the Lagrangian dual, that is fx minus lambda g is equals to lambda Lagrangian of lambda and x. So actually what we will do is that minimize this thing with respect to w and b, and maximize with respect to alpha i's that are taken in case of these wrongly taken points. And so this can be written in the form that you have in the paper. Yeah, so this one, actually this one is the for the points. This is actually we have to minimize this loss, minimize this error, and we have to maximize the margin. So this is actually the objective function that we have. And this is a soft margin hyperplane because we are considering that we have some errors, and we will have to minimize those errors. And actually after applying the Lagrangian dual and differentiating with respect to the omega and b and making it 0, we can obtain this one, that w naught is equals to summation of L yi alpha I into xi. So why actually the computation reduces is we only take the alpha i's to be greater than equal to 0. Alpha i's are greater than equal to 0 only for the support vectors. And what is support vector actually? Support vector, as you can see, I have noted here that the vectors that just lies on the margin are known as the support vectors. So we will consider alpha I only greater than equal to 0 for only the support vectors, and all the other vectors alpha I will be considered to be 0. So that is why the number of computations that we require is getting reduced. This is the actual reason of using the dual rather than the primal problem. So after that, uh, now there comes another problem, that if this cannot be separate, as I have told earlier, that this cannot be separated if the data is in a non-linear distribution. So what we will have to do is, like, we have to shift the space. We have to shift the space such that we can go from lower dimension to higher dimension. Like you can see intuitively here in the two-dimensional plane, that this can be easily separated by a circle. But the problem is that we have to find a hyperplane, that is a plane and that should be linear rather than a circular. So what we will be doing is we will be increasing the number of features that we have. And how we will be increasing it is by taking the inner products of the features that we already have. So what we have done here is we have basically done if let me take it as a, and like x minus a whole squared, if I take all of the terms to be squared up and add those up, then what we will see that these will go above the plane, that is z. So this portion is strictly above this plane, and this red portion is strictly below that plane. That is why if we change the dimensions by using some non-linear transformation on the data points that we already have, we will be having a much simpler time solving the classification problem. So as you can see here, that when we had earlier we are doing SVM fit x and y. So it was actually doing the computation for x and y, and the xi's were the vectors that were involved in the two-dimensional space. Now we are applying a function f of x that actually increases its dimension from 2 dimension to 3 dimensions. Here in this case it is 3 dimension, but we can have higher dimensions as much as we can. Like if we have x1 and x2, for example x1 and x2, we can have like for each vector like two features. So we can have one x1 x2 x1 x2 and x1 squared and x2 squared. So these many features we can have if we just increase one dimension of the uh, feature vectors. So using this we will be dealing with the so what we will be actually doing is taking the input vectors, we will transform it, and then we will be applying the classification model. But now now we are applying asm, but now the problem is that when we are applying the transformation, the number of features that we are having is very large. So the computation again increases. Now to overcome this problem, that so much of computation, we will be using the kernel, so that we can bypass the transformation process altogether. So for that you can see here, like here, these are the two vectors like xi1 and xi2. These are the two features, I applied the transformation T, and I just take it to a higher dimensional space. Now it has already 1, 2, 3, 4, 5, 6. So we have 6 features, and then we have to apply SVM on these all 6 features. Rather than so the actual computation will be n cross p. The p is a feature and n is the number of samples that we have already. But what actually we will also have to find the inner dot products between all of these, so that we can find the closed form equations. But what we can do, rather doing that without transforming the data, we can find the inner products of the original data, that is the xi1 and xi2. What we can do is we can find 1 plus xi1. This is the polynomial kernel that we are applying here, that 1 plus xi and xj, we just dot product both of them and make a square. So when we are squaring these, we are getting directly the transformed inner products that we will be getting, like uh, all those terms that were present after doing the transformation of t of xi and t of xj. If we multi dot find the inner product of this, we will be getting the same as what we are getting from this. But what is the difference? While we are using this, we will be having p features multiplied with n times the number of samples that we have, rather than this, which is only having this xi xj. The number of products are already reduced because the features are lesser in the original input space. So this kernelization process of SVM reduces the number of computations that we need to do to get our actual SVM model working. So that is why we are using kernel and transformation here. So after that, there is some slide where we can see that this is actually a signal. So this signal is convoluted with this response signal. So if we do the convolution of these two signals, we are getting a new output, this one. So what will be our objective is to find such a response such that this output should be in such a way that the finding the hyperplane in that output will be easier. So this is the actual idea behind kernel, so that we can reduce the number of computations that are going behind each of these um, method. So after that, let me come to the point, like why actually it is a linear combination of the uh, support vectors. So here we can see, while we are solving the dual problem, we took an assumption that all the alpha i's that are not on the margin are zero. So actually you can see here that the w naught, that is basically the weight of the hyperplane, is basically coming from the linear combination of xi's, and these xi's are only of the support vectors, and all others are zero because alpha i's are zero for all others. That is why I said that it is a linear combination of the support vectors rather than the all of the vectors. So also this is also already described by me in this TL that if we put d equals to 2 here, it is a polynomial of degree 2. Rather than this, we have also the radial basis function, which is given by this, and this is the transformation actually, but this is the kernel given with the kernel that we have for it. So this works great on all of the data we have. That is why it is one of the best of the self supervised learning algorithm that we have with us. And using this kernelization technique and uh, the dual problem solving method, we will be using it as the main algorithm for the networks, and that is why it is known as a support vector networks, and which uses basically the algorithm of support vector machines. So this is actually the summary of or the paper that we have with us.